in any case, so we will be, so let's first, so we're one-way functions.
So they are
In
well
order to
known
start,
in cryptographic settings. But now I think Levin has some strange similar question, superficially similar for general recursion theory.
yeah, so I suggest to, well, what's the general, philosophy of one-way functions? Functions that are easy to compute given an input, but then given an output, it's hard to find any input that, gives this out. And how it's formalized in computational, in cryptography, and computational complexity. Let's start. Well, let's start. Well, I guess let's just remind the one definition of one-way functions in cryptography and computational complexity and so on. And nobody knows whether they exist or not. One-way functions in computational complexity. So, well, that's more formally, it's a family of functions. So I give a definition of a one-way function. A one-way function.
Which probably isn't strictly necessary for the sequel, but important anyway.
Huh?
It is probably not strictly necessary for the sequel, but it's anyway important, so let's call it.
Yeah, I guess let's try to do this because to have a understanding why what will be in the sequel doesn't solve this problem, for example. Existence of one field function in computational complexity. Yeah, there's the question, I think.
Where is the question?
Okay.
Viali has raised a hand, but is already dropped now.
Yeah, okay. So a one-way function is a family of functions, Fn, where Fn goes, I don't know, from 0, 1 to the n, from n-bit strings to some polynomial in n-bit strings. Where P of n is some polynomial. Which is polynomial time computable. So, well, so you have a n-bit string input, so you understand which n, and then there has to be an algorithm that given an n-bit string outputs the out fn of x. But there exists no randomized polynomial time algorithm A, which is supposed to invert it. So there exists no randomized polynomial time A such that, so what is happening? What is happening? The idea is that what we want to do is we want to take random x. So let's see. So well, there is an algorithm A. It receives. It's supposed to receive f of n of x, where x is drawn at random from 0, 1 to n. And it also receives its internal randomness, maybe. And it's supposed to output some y such that fn, well, let's better call it, not to confuse with outputs, x hat x hat such that fn of x hat is equal to fn of x. Yeah, and x is again a sampled uniformly random. So if the algorithm outputs x hat, so it's not necessarily the same x, but it's any, I mean, it could be that the image has many pre-images. Could be any x hat. So if this happens, then well, that's like the algorithm served its purpose, so has succeeded. So we want to say that the one-way function, well, if family of function is a one-way function, if it's polynomial time computable, and there exists no randomized polynomial time algorithm that has this probability of success, well, I don't know, let's say bounded from zero by some reverse, where this probability of success grows like a reverse polynomial. So what I want to say, there exists no randomized polynomial time algorithm and no polynomial Q
No, if there exists a polynomial Q such that there is no randomized polytime algorithm. Actually, there are two notions. You can say that to do it almost everywhere is difficult, and to do it for a reasonable part is difficult. It's called of weak one-way function, strong one-way function. So I don't know what you want to,
Yeah,
to
but then
say.
we know that it's the same. Yeah, so I want to show that they well, I want to say something because I like, let's say it will be more closer to what I will say next. I want to say that there exists a condition. Sorry, a condition is that there exists no algorithm that does it with any like reasonable probability of success.
So for every
So I'm,
algorithm, the probability of success goes to zero faster than any polynomial. So it's strong one-way functions. So
yeah.
whatever algorithm
Well,
you
so I
invite,
started writing it as follows. So the probability. Okay, let's write it like that. But there exists no randomized polynomial time.
no, it's better to say
Well, I
that
don't know.
for every randomized
You're gonna
polynomial
confuse me.
time, the probability of success, it's better to say without excessive negation. For every polynomial randomized
Okay,
algorithm,
so let's try such that for every polynomial randomized algorithm A, the probability of success that can be written as follows. So we can assume that the algorithm receives, first of all, the length of the input written in unary. Then it receives fn of x sampled uniformly at random and some randomness. So the probability that this thing applied again, if I will be so where x, so again, so the algorithm receives fn of x and its randomness. And also the length of the input written in unary in order to understand for which n, because, well, it can be that p of n is the same for maybe for some different n. So let's just do this.
yeah, it's better to assume this, but the number of randomness bits can be larger than n. It should be polynomial because the logarithm is polynomial, but
Yeah, well,
it's
okay,
not
so
necessarily n.
it's so where x is sampled uniformly and random from 0, 1 to the n, and r, I don't know, from depends how many random bits it should sample the polynomial time algorithm. So this should uh,
Go to
go to
zero
zero,
faster than any
go
polynomial.
to goes to zero faster than any reversed polynomial.
So, for example, it's if this probabilities, I don't know, for some, if for some n it happens with probability the inversion happens with probability 1/10, it's bad, it's not allowed.
If for some
If for,
n what?
if for infinitely many n the reversal is possible with probability 1/10, it's not okay with this
It's not a
definition.
one-way function then.
Yeah, yeah, yeah.
Yes.
Not a strong one-way function.
Yeah. Okay. So that's a standard definition. And so are there any questions here? Okay. So then let's try to give 11th definition of one-way functions. Well, maybe, okay, one-way functions for infinite strings of zeros and ones. So first of all, we will work with the notion of computability. So there will be, so we will
No time
say,
bounds, nothing, just computability.
yeah. So if I have a function that receives an infinite sequence of zeros and ones and outputs an infinite sequence of zeros and ones, let's agree what is a, well, I mean, I guess more or less we all understand what we mean by that. So
But
it means that
it's important that you assume that the values are always infinite, or you don't assume.
I assume that the value is always infinite.
But this means a lot of, this is a very strong requirement, because this means that actually it's TT reduction. It use only no computable number of input bits to produce every specific output bit. No, I don't mind if you want this, let's be this, but it's quite strong requirement.
It's computable with Oracle Turing machine.
No, but if we assume that this function is total, then the number of bits from the oracle needed to generate bits number n is a computable function of n.
Okay, yeah.
Because we can make a search until we find a cover of the entire space by the enough things. So it's what's called TT reduction in computability theory.
Yeah, I guess so far it doesn't contradict what I'm going to say next.
No, since you will say that it doesn't you will show that they exist or they don't exist.
That one-way functions exist.
So it's stronger result. But then you need to be sure that it's total. Okay.
And it will be total. So a computable understand that there is a Turing machine that starts reading bits of the input, and from time to time outputs new bits of the output, let's say.
Yeah. But what I am saying, sorry, just I want to stress that what I am saying, that if it's total, if it produces always an infinite sequence, then it uses g of n bits to produce n output, g of n input bits to produce n output bits, when g is some computable function.
Yeah, I think in our construction, this will be polynomial time computable, in the sense that to compute n bits, you need to run, I don't know, 2n bits maybe,
Okay,
and polynomial time.
Yeah.
Okay, so everybody more or less agrees what we understand by computable functions of that sort. They might be not total. For example, for example, if there is, for example, the function is not defined and the Turing machine, it never stops working on some input, that's also fine.
No, I don't understand.
I mean,
So
but then it's not total.
you assume that they are total or not? your one-way function will be total or not?
One-way functions will be total. Algorithms for reversal will not necessarily be total.
But of course you can consider algorithm. It gets an infinite input and can produce bit by bits, but it can produce finitely many bits or infinitely many bits or no bits for some inputs. So this is just an oracle machine.
Let's just write it. One-way functions total. Okay, so let me just try to give a definition of a one-way function for 0, 1, for infinite strings, and then we'll see if it works or not. So a one-way a function f, a total computable function f from 0, 1 to the naturals to 0, 1 to the naturals is one way if, so now I want to say, okay, if for every randomized algorithm A, so A now will obtain an input, which is an infinite string, and also another infinite string that is its randomness. And it's supposed to also produce an infinite string.
No, but it's not necessary. It produces finite or infinite string.
Huh?
It produces finite or infinite string. Let's
write it here like this.
And it's just a standard Turing machine, oracle machine, which produces bits one by one. But it could happen that after some points, no output bits are produced.
Yes. So, it's not necessarily, well, you just said it, it's not necessarily total.
No, in this way, as you write it, of course, it's total, but the values can be finite also. That's, as a function, it's total technically.
Yeah, okay, so let's
we know. What does it mean?
Okay, let's not write this. And we indicate that it not necessarily, it might, might halt after reading some input sequence, might not halt by the fact that it can just produce finitely many bits on some inputs. Okay. Yeah. So if it is clear, so now I want to write that the probability of the success, like converting, should be 0. So let's try to write it. So what the algorithm supposed to receive? The value of the function on the uniformly random input, and also its randomness. And the success is when this string is infinite, and f of this string is equal to f of x. So in this expression, I implicitly assume that this also states that this thing is infinite.
Because we cannot apply f to finite strings.
Yes.
And then probability taken over a, x, and r.
The probability taken over x and r. X, uniformly at random. Well, both, let's say, uniformly at random. From 0, 1, well, it's is 0. So if for every randomized algorithm, the probability that this algorithm given f of x on random input gives some x hat such that f of x hat is given f of x is 0, where the probability is taken x is random and the randomness of the algorithm.
So let me try to think about this. So you have kind of two spaces. You have spaces where the x lies, and you have space where f of x lies. So the algorithm gets f of x, and so it can look, for example, to get some specific prefix of f of x, we know that we know where it happens. So we know some strings which are necessary and sufficient to get this on the output. And if we get a longer prefix, we have a longer, we may need more input bits, but all these cases should be under these cases. So essentially, we have some kind of infinite computable tree. It's actually given to us, more or less.
Yes.
And we need to produce a path in this tree with non-zero probability. Am I correct or not?
Let me think. So what is a tree?
No, we know let's take some prefix of x. I don't know, the first bit of x. And then we know how many input bits we need to compute the first bit of x, like 10 bits, for example. So this is
Wait.
one
We
bit.
are given f of x.
Yeah.
We are given
so knowing
f.
this first bit of f of x, we can find which, I don't know, 10 input bits are needed to produce this first bit. So we have some subtree here. And then we have some extension. We have the second bit. And we need, I don't know, we need 10 more bits, for example. And we know exactly which combinations of 20 bits are okay. And of course, this for these two output bits. And they should be, of course, some extensions of this. So we get next layer of the tree.
So we get a computable tree.
No, it's not computable because it depends on f of x. So for every given f of x as an oracle, as an input, we can compute this tree.
It's like
this is computable.
And the branches are, infinite branches are pre-image of f of x.
Yeah, infinite branches are exactly the sequences which are mapped to f of x.
Yes.
So we need our algorithm, if it should use randomness, just to produce, given a tree, or being able to compute a tree, it should compute a path in this tree, which will have non-zero probability, generate a path which will, with non-zero probability, belong to the tree, yeah?
Yes. We want, well, I mean, for instance, we might want just to produce some, let's say deterministically. But if you can do this with some 99% probability, then it's also fine.
No, you should not be able to do it even with a 1% probability. The probability should be exactly 0.
Right. But I mean, yeah, you having a computable tree. So is there a computable branch? Even
no. So let me say a few things which I remember about computable trees. So let's go to the page 3, if you can. So it's easy to construct a computable tree with no computable paths. So for example, it can be done like this. So we can take, let's start with a disjoint inseparable enumerable set. And the tree, the infinite branches are those which go left at the level which belongs to P and should go right at levels which belong to Q. Of course, P and Q are not computable, so we cannot prohibit just going on the left if n belongs to P. But at some point when we see that n belongs to P, we at some level, maybe far away, we prohibit everything which goes left at this n. So it's a kind of closed set. We just cut parts of it when we see that n belongs to P, and other parts when we see that n belongs to Q. And so we can construct a computable tree where infinite branches are exactly this paths. And because they are inseparable, there is no computable branch.
Mm-hmm.
And now the question is, can we generate, imagine we have some computable...
Sasha, wait a second.
Yeah.
And when you talk about computable trees, what do you mean? It seems that your tree is enumerable, not computable.
No. I may. So computable tree is fully computable tree. We know what is allowed at every level. So it's computable in the strongest sense.
And how do we know what is allowed at every level?
No, but no. The tree is constructed like this. First, we allow everything.
Right.
But when we see that some n belongs to P, then at the moment when we see this, we cut all the parts when the branch went to the left at level n. We cut it actually much higher than n probably. But still, because to know what is cut on the first t layers, we just wait for time t.
I see.
So it's fully computable, but on the level of infinite branches, it's the same. But that's... And then the question, which I should know, and it's a shame that I don't know. So the question, is there a probabilistic machine generating solution, generating a separator with positive probability? I guess the answer should be no. So there is not only a deterministic machine that computes a separator, no, even a probabilistic machine that computes a separator with positive probability also, I guess, doesn't exist. And
so
unfortunately,
that the separator may depend on the randomness.
Yeah, of course, separator may depend on the randomness, but we want the probability that we really get a separator
is positive.
Yeah, I think it should be zero. But maybe, Bruno, maybe you remember why it's the case.
I'm thinking.
No, it's a general big theory. So we have a Medvedev problem. It's for a tree. So we have some kind of infinite path, and some of them are probabilistically solvable, but not deterministically solvable. It's normal. For example, we can construct a hyperimmune set with positive probability. But I think this one we shouldn't be able to construct. Oh, and Laurent explained me 1,000 times, but
He explained you why the probability is 0.
No, I guess. Or maybe he explained me that y probability is non-zero, but I think I think that it's still 0. My intuition is like this. Because imagine, it means that imagine if it's not the case. Then let's imagine that P and Q are provable and irrefutable problem in piano arithmetic. Then if we can separate them with positive probability, also we make this, as usual, we can make this probability 99% by choosing the set of inputs when it's okay. And then we get a program which solves every, proves or refutes whatever can be proven or refuted with probability, which separates them with probability 99%, which will be too good to be true. But it's a shame. We should. I think there was even maybe this was a kind of Levin once explained that this Gödel theorem is not so strong as people believe, because imagine that there exists something like this, then it will be more or less essentially the same if its probability of error is too small, it will be a nice thing and so on. Also, we can make amplification probably.
So once again, so you want to show that there exists no algorithm
which generates a sequence that separates P and Q. If P and Q are enumerable, not.
And what you said, provable and disprovable, or what?
No, I said that why I believe it's not, such a machine doesn't exist. Because if there exists a machine which does this probability 1%, then also there exists a machine which does it with probability 99%. As usual, we can just fix some part of some initial segment of the randomness so that this 1% set have density 99% inside this interval. And then we can use it to decide decide the truth of an arithmetical statement by, or set theory statement by applying this machine. And we know that if the statement is in fact independent, then the machine can do whatever it wants. But if the statement is provable or refutable, then we will get a correct answer, whether it's provable or refutable, with probability 99. And this would be almost as good as if the Gödel theorem was false. And I guess the Levin has special, he stressed this in some paper, but it was all long ago. And I forgot everything.
Well, I don't know why we can run randomness and get to see whether for 90% of these things it's like.
Sorry?
I mean, if we have a randomized this thing, then we have a deterministic, or I don't know.
No, because we need to compute the infinite path, and for different random variables, different values of random sequence, we have a different path. They all separate P and Q, but they are different. So we cannot generate any computable path. No, it's not possible.
Okay, I'll try to continue them.
Okay.
But do you agree that if such a thing exists, then we get a one-way function, because it seems to be a weaker property, kind of non-uniform.
Which
No?
things exist?
If there exists, if the probability is really zero, if the answer is negative, which I assume is true, then it would be answer to Levin's to the one-way function in your sense, no?
No, I don't understand this.
So Sasha, explain why does it imply
Okay,
the
because
answer?
what Sasha says, that we can for every sequence x, we should find a preimage of the function f of x.
Right.
Sorry, let's start again. So you want to show that if there exists a computable tree where there is no randomized algorithm that with probability 1% gives a, well, with positive probability gives a branch of this tree,
Yeah.
then there exists a one-way function.
In
Right?
the definition, as you say, yeah.
And so you guess you want to start with a definition of this one-way function, given this tree.
Yeah. So no, but let me try to explain why it happens philosophically. So preimage is a tree, more or less knowing the f of x. We just know the tree, and then
Sasha, which tree? Preimage tree?
preimage tree of f of x, and then we want to find
Yeah, okay.
some element of this branch in this preimage tree.
So why do we know it? Because if we have some string, we apply our machine to compute the image until
on all branches we know which strings of length n appears. And then we know the preimage tree. So somehow what you are saying, in what is required from the inverter is just to find elements in all preimage tree with positive probability.
Yeah, but I mean, I guess you have one tree which is hard. You now have to construct some, I mean, like a function or something.
So
Under the. So how? I mean, I don't know. What will be the function? Such that this tree, which is hard, appears as a preimage tree, like something like that. I don't know.
So you say that this preimage tree cannot appear often. That's what you are saying. So
Well, I don't know.
Cannot.
It's like, wait. Yeah, I don't know. Maybe somehow we can do that.
I don't see where the randomness comes into play. So we somehow need to use that the probability to find an infinite branch is 0. So our randomness should be the randomness of some algorithm that tries to find it. But there is no such a fixed algorithm. We know that there is no one.
No,
right?
So you're explaining what now?
So I don't see any one-way function which is naturally related to the tree.
Yeah, so you have a difficult tree.
Right.
And of course you can construct a function that
I don't know.
So for example, we can take a zero sequence as an image, And we can assume that f minus 1 of the zero sequence is this difficult tree.
Yes.
But then we also need, okay, we need, but okay, but if it's, yeah, but for other inputs, it will be easy, maybe an easy tree, and it's enough to make a correct inversion for this other inputs.
Yeah.
Okay, so I think we should think and either ask Laurent, or maybe we can invent the argument to prove this no. It is I think it's a very important statement, and it's a shame that we don't know the proof. But so please tell us next time why it doesn't exist. But indeed this doesn't solve the problem about one-way function, which is somehow more difficult because we need to deal with
or more easy. I don't know. It's
in different directions. Yeah,
because somehow I will just construct this function. I don't know. No inseparable things. Okay. Like
okay.
just so theorem one-way functions for infinite sequences of zeros one exist. That's and the proof is by Barmalias-Zhang. So let's
And
try.
also Peter Gatch solved. He explained me that he solved also this problem independently, but his result is somehow weaker, and it would be interesting to understand what is the difference. But okay, let's start with this.
Yeah. Well, so let's construct. Let's give a definition of a one-way function. So
We already have the definition.
well, sorry. Construction of a one-way function.
Okay.
Construction.
Yeah.
Construction.
Yeah.
So, well, okay. So we want to define some x. So it reads x1, x2, x3, and so on. And it's supposed to output y1, y2, y3, and so on.
Yeah.
Okay, well, let me just try to define it, and then we will see what happens. Well, first of all, we fix a computable bijection between pairs of natural numbers and just natural numbers.
Okay.
And now I want to say, okay, and now I will assume that indices are, pairs, natural numbers. And I want to define what will be the bit with index which corresponds to a pair ns.
Yeah. So actually construct not a sequence but a table. Very good.
What?
No, we construct a two-dimensional table as an output of f.
Yes.
Yeah.
You can say like that. Yeah, but I will also assume, okay. So I will say that this is x to n if the nth program halts in exactly s steps. Otherwise, it will be x to ns plus 1. Okay, so let's try to understand what is happening here. So I have x1.
So let me try to draw something. So there is this y and s. So there is n, and if the machine stops at some s steps, then we have some specific thing which is x to n, strangely.
Yeah.
And here we put, in all other places, we put different bits from x.
Yeah.
So we can start just with, we put x in a table, one half of, so x is consists of two parts. It's an odd part and it's an even part. So the odd part is just written in a rectangular plane, yeah? We just copy the bits of x
Yeah.
in this table.
So basically, yeah. So first of all, one remark. Let me give a simpler remark. First of all, every bit of y will be some bit of x, and this will be an injective function. So different bits of x, some bits of x will be lost, but I mean, every bit of y uses a different bit of x.
Yeah, so this part means that we some bits. So first we use the odd bits of x to fill the table, and then we make a very careful replacement for one bit in a column. We replace it by the even bit.
Yes.
Using the other half
point
of
is that
x.
sometimes we use these bits, even bits, for a very large. I mean, this could be that the nth program halts in in a huge number of steps s, and we will then, in this case, we'll use x to n for some very distant bit y.
So we make a change in nth column if the program terminates. But if the program terminates after a very long time, then this change will be very far away. So it seems that it's more or less obvious why this function is computable. Because we just, to need specific position, we just need to check whether it finishes in a given number of steps.
Yes. Well, I just wrote the definition, yes.
Yeah, but what is not clear is whether what depends on halting problem, whether the nth column is just exactly taken from the odd bits, or some very far bit is taken from the even part of the x.
Yes.
Okay, so is it clear now how the function is defined?
It is.
It is. Bruno, is it okay?
Yes, and
But maybe that now some of you can explain why it has no inversion. Because we know that's computable, the only which remains is why it's not why there not exists the probability of reconstruction and is zero.
No, I guess that somehow the halting problem reduces to this, to the problem of inversion.
Okay,
but
so
wait,
let's assume that...
Wait, but we can't just use that the halting problem is not solvable, because here we need to show that the probability of inversion is zero, right?
Yeah.
Yeah, so we have to somehow show something bad, assuming that this thing has positive, the probability of inversion has positive measure.
But let's try to prove.
Yeah, I can enumerate the first step. Assume A is an inversion algorithm,
which is succeed always
with positive probability of success.
With probability 1. I would.
No. We need to get a contradiction. So we need to assume that it's a positive probability.
But let's try to solve a simpler problem first.
No, but I think that inverse image is 3. And if we take a random string, then finding correct path from 3 is equivalent to solving halting problem if x is random. I guess that's how they prove it.
Okay, so you suggest to start with a simple case when it's probability 1, or just deal with general?
With probability 1. So whenever x is Martin-Löf random, it would be my first attempt. If x is Martin-Löf random.
Can I make a very simple remark, first of all, because it would simplify things, I think.
Yeah.
One observation that if the input is random, uniformly random, then the output is also uniformly random.
Okay.
Because whatever is happening, we just copy some fixed bits of input into the output.
Now, so we want to show that the probability, well, okay, that it's 0 probability of success, or it's less than 1 or something, but it's enough to show that. So we assume that algorithm receives a uniformly random string y and r, then it should give, applied to f, this should give us this y. So it's just, so we want to show that it's 0 or, well, at least it's y is uniformly random.
And now we just need to reconstruct y, because y is just image of f.
So, okay, we need to find something that will give us this y, if we know this y. And, okay, let me try to, why at least, because the formal algorithm, they use Lebesgue density theory.
Just wait a bit. So you are trying to explain what now? Why?
Let me then stop talking.
No, but just say what you are trying to explain now. You are proving what?
Okay, I explained one thing. I can try to listen to somebody else, or can try to continue the proof.
No, let me check whether I understand correctly. You explained that all we need to prove is just to prove that there is no.
I just explained that the distribution on the output is uniform. It means that we can assume that the algorithm receives a uniformly random string, and its task is to produce something that applied f gives this string.
So
and
in general, we would
that
write f of x here, and we will have f of x. But since it's uniform, we can consider this, yeah?
Yes.
And now you will prove why this probability is 0.
Yes.
Okay.
So let me try to prove it. So the method is to use Lebesgue density theorem. Lebesgue density theorem says that, well, okay. What does it say? So okay, let's denote this set of success set like this. The set of y and r such that f of a of y and r equals y, right?
Yeah.
So let me try to see. So Lebesgue density theorem. So it says something like that. For any measurable set S, for almost all points in S density of, so for almost all points X in S, density of S at X is 1. And what is density of a set at the point? So the idea is that I have a point, I take a small ball around this point, and I just see how much of the measure of this ball is taken by the set S. And I take the limit. And if the limit, so, and the statement is that for almost all points of any measurable set, density of the set exists and is 1.
And for almost all points outside of the set, density is 0.
Yes.
Limit density is 0. Yeah.
And I mean, in our case, we don't take balls that converge well. We just, it means that density, I don't know, density of the
I'm sorry,
set
do you mean
S,
that the measure of S is positive?
No, if it's negative, then for
well, if it's 0,
almost
then
all
I mean the
points it's
statement is
trivial.
breaking. It means that the measure of points of set of points of S that do not satisfy this is 0. So with
Has zero. I
set
see.
S has
Sorry, sorry.
0,
I
then
see.
it's fine. So density in our case is just the limit. So we just take large n, we fix the first n bits of our string, and we take the cone that contains the first n bits of our strings, we intersect it with S, and we take the fraction with the measure of this cone.
No, but now we have sets two-dimensional things, so we can do this, choose this fixed bit in some order, but it's okay.
Yeah. So now we have 2 dimensions, so we have to fix like the first n bits of one thing and the first 10 bits of the other.
No, the first bit in n times n squares. We will fix bits on the plane.
No, I think it's
Okay.
what? We have 2 infinite strings on input. Y and R.
Yeah.
So our set is a set of pairs of infinite strings. It's not 0, 1 to the n squared.
Yeah. What I'm saying that one of the strings is actually a plane, not a string, and so it depends. Technically, it depends on the ordering on the bits on this plane, but it doesn't matter.
Yeah. Okay. So
How I want to use this theorem?
How we want to use this theorem? So we have a set success that we want to show that has 0 measure. So the way we show this lemma halting problem is reducible to every, well, like Turing reducible element of success that such that density of this set at this element is 1. And then, so we show that almost all halting problem is reducible to almost all points of the set success. And then there is another fact that the set of strings to which halting problem is reducible has measure 0. The set of strings such that halting problem is reducible to S has measure 0.
No, but this is what is called the Moore, Levin, Shapiro. So if a sequence is not computable, it cannot be computed with a positive probability by a randomized algorithm, because then we make a probability close to 1.
This also somehow uses a weak form of Lebesgue density theory.
Yeah. No, but actually, almost definition of measurable sets, but okay.
Yeah. Okay, so, yeah. So are we happy with the fact? I mean, then dilemma. Really, what's new is dilemma, right? And what's remain to show. I can explain also how to prove this fact. Also, it's not difficult.
No, but we already said this, because we know if it's positive probability, then we can make it close to 1, and then we can use it to determine, just find the computable. It's more or less obvious. But what is not clear is the lemma. What is strange in the lemma, if the density is 1, how can we use this fact? Because density is a limit, and we don't know anything about the convergence speed. So how can we use this fact?
Really, we just need. So we will show this. The halting problem is reducible to any element such that starting from some point, the density is at least 90%. So let's try to write it. Halting problem is reducible to every element of success such that density is at least 0.9 starting from some n0.
No, but look, then it's just exactly the same argument. If the density of the success, if the measure of success set is positive, then there exists some interval when the fraction of success set is 99%. So if we restrict ourselves in this interval, then the probability will be 99%.
Okay. Well, it's already 0.9.
You did not use that this density is, I guess you didn't use that the density is big starting from some point.
I need to use that it's at least 0.9 from every.
You need in every.
Yeah, that's the not just that there exists a cone.
You need that every small enough cone. Yeah. Okay.
Yes. That's the difference, I think. That's a real. So okay. So we need to reduce halting problem. So and now I have an element which is a pair YR of the success sets with this property. So and I want to solve the halting problem with the oracle to this pair.
Yeah.
Okay, so first of all, so I need to give an algorithm that solves halting problem with the oracle to this y in R. First of all, I assume that this algorithm knows this n0. Well, we can, okay. And then, okay, so the algorithm, it receives on input the nth program. And it wants to say whether it halts or not. Okay, so what it starts to doing? The algorithm, so how to say? So we have an inverting algorithm, and we have this thing that's supposed to solve the. Let's not confuse it. So, so what we are doing, we start running A on Y and R until so what is happening? We run A on Y and R, and it's supposed to give us this x1 head, x2 head, and so on. That apply. The idea is that when we apply f to it, it's supposed to give us y. So until we produce x to n. And this will always stop because we know that y and r is from the success set, so it has to produce an infinite sequence. Okay. So we produce, well, let's see what, at this moment, let's look how many bits of y and r we have used. Let's say that this is at most m bits. We used m bits of y and r to produce x to n. And we can always assume that m is at least n0, because if no, we can, I don't know, we can read a few more bits of y and r. So now, so now these indices so so now what's the idea? I want to look at this sequence and
then change some bits from y to check whether also the inverse changes.
Yeah. So let's try to think what's happening here. Let's try to think what's happening here. So we run y and r for that many bits, and we know that actually 90% of continuations of that stuff is also reversed good by the algorithm A, right? But what happened already? We have run x1, so we have run our inverting algorithm on this infinite sequence, and we have already produced x1, x2, and x to n. So the point is that this x to n, it can be actually So if this is a preimage of this thing, then it either, so the point is that x to 1 can go somewhere here if when x to n is used. So because the point is that y and s is equal to x to n if nth program halts in exactly s steps. So, well, let's see. So this means that if the nth program halts at some point, then this bit can be used. I mean, this can be used for one of these inputs, or it can go somewhere there, right? If the nth program halts in very long number of steps. So I want to ask why it's impossible that it's really why s cannot be very large so that x to n is actually points out somewhere there to some prefix that we haven't already read.
You want to say that then the prediction with probability more than 50% will be impossible, something like this.
Yes. Then only 1/2 of continuations will be correctly inverted, right? Because we have already said that x to n is this. So we can only get our initial y if x only for those y's that have this x to n somewhere there. Is it clear? It's the most important thing here.
No, I really cannot follow the detail, but if you say just finish, I guess you are close to the end. And then if I think I should think about
so
construction.
I mean, that's it. So given the nth program, it means that if the nth program halts, it can only halt in some number of steps that we can compute. It's like if we look at these indices that we have here from 1 to m, it can halt in, well, I mean, then if you look them as pairs of indices, there is the largest s that you can meet within the first m bits, within the first m indices. And it means that you can run the nth program only for these s steps. And then if it doesn't halt, it cannot halt for more steps, because otherwise the fraction of continuations that are inverted is at most 1/2.
Yeah, so Bruno, do you understand the proof in details? Maybe you can then repeat it and
I can only repeat what Sasha said. I don't know how to say it better.
no, but you're convinced and that is correct.
More or less convinced, yes. Okay.
Okay, then try to repeat it. It will encourage Sasha at least.
Okay, so
at least someone understood something.
But wait a bit. Maybe somebody can explain me the following thing. Assume that we have an algorithm that inverts our function always with probability 1 on all the inputs. How do I solve a halting problem then? So we do not need Lebesgue density theorem for that. We just explain
Okay,
simple thing.
Yeah. Okay. So yes. So we look to the use of algorithm to compute x to n, and then we check algorithm for this many steps whether it halts. If it halts, we say.
But wait.
Of course,
You said this many. How many?
the use. So how many bits of y were used to compute x to n?
Okay.
Okay, so it gives us some number and it's called m in the picture.
Okay.
And then we run program for m steps, or maybe m squared or something. So we run this many steps. If it halts, of course we know the answer. If it doesn't halt, we say it will never halt.
And why is this?
Because if it never halts, then it takes a value. So x to n is computed from so so if it halts later, then if it halts much later, then value x to n is equal to value of y in very far place.
Yes.
So then,
And so we somehow computed, you say that we computed the value of, actually computed the value of y before using only small part of y.
yeah, and
So
so
we
if we
computed value which is not defined yet. Somehow.
Exactly.
That's
yes.
what you're saying.
Yeah. Defined in the input, which we have seen. So if this very far place, if we flip the bit, then also bit x to n is flipped.
No.
So it
wait a
means our
second.
algorithm makes a mistake, but you said it's always right.
Okay. Wait. So I want to find out whether Pn holds.
Okay.
So I apply the algorithm to which y? Let's start with this. So which y I do?
And lemma says consider yr that is
assume that we have a deterministic algorithm, no r at all. So which y I use? Any y.
So no, we want to prove technical lemma that says that there are very few YRs for which algorithm maps to Y. The output of algorithm is Y.
But
it's
of course, you can assume that algorithm doesn't depend on R.
You want to show that there is no algorithm that just for any y?
For any R and Y.
Yes. Forget about R. There is no deterministic algorithm that inverts our function everywhere.
Yeah. So you just you use it like for zeros. So you're then
I take all zero y.
Exists?
I take all 0 y. Then what then?
Okay, you have the nth program. You want to know whether it counts or not.
Right.
You run potential your inverter on the string of only zero. So y is all zero. Run 0, 0, 0, 0, 0 until you get the first 2 n bits of the output.
Right. And then
you see, well, how many bits of the y you have used. Some number m.
Okay.
Then you see, well, what is the, so these indices of y, remember, they are also presented as a pairs of natural numbers, n and s. You take the largest s where that appears in the first m bits. You run the nth program for that many steps.
Okay.
And if it halts, then it halts. If it doesn't halt, you say that it doesn't halt.
Why?
Because otherwise, if it halts, but for a larger s, this means that x to n it means that when you apply f to this already prefix that you have obtained.
So all zeros, but in as n you replace by 1, your algorithm will be wrong.
Yeah, it
If
will
you flip this very
fix.
far,
It will only be then. It will say that f of this thing has to be x to n on some very in some distant position that it's not that you haven't seen before. But when you so you can give it your algorithm this input with some other with not x to n. But in any case, it will not see this. It will only read the first m zeros, and it will say that x to n is, I don't know, 1 or 0. 0 probably, I guess.
Mm-hmm.
But then you see that it will be wrong on this sequence where it has 1 here.
Mm-hmm.
No, I guess we should better understand the definition of A and be accustomed to it, and then it should be somehow. So it seems that there is, if it's true, it shouldn't be difficult because it's just we see how the density
Well, I don't know. Who understood
theorem.
the argument and so on?
Sorry.
Who understood this argument? I want to ask.
okay, I more or less understand the argument, but I should think a few more times to really believe it. But also, I don't see why we need Lebesgue theorem. Why can we not
Just first,
do it
people
directly?
don't say Lebesgue. He's Lebesgue.
Ah,
Even
Lebesgue,
in Russian,
yeah.
in French, in English, don't I cannot. Yeah, okay. So how can we avoid it?
Yeah. Oh, sorry. Yeah. Okay. No. Now I understand. But
No,
then
there
we
is a
need to do
we just
something else.
we
Yeah,
need
yeah.
not only density in some interval containing point, but in all intervals small enough intervals containing this point. This is the
Yeah. And but then maybe compression argument with Martin-Löf randomness could be used. But okay, maybe then one can argue what is most ugly, thinking about proof of Lebesgue or use compression argument.
But by the way, who knows the proof of Lebesgue theorem? I don't.
Actually, I
I know.
tried to
But somehow
recover the proof, and I failed. I don't know the proof now.
I mean, I can try to say, but it's very strange. Somehow I use martingale inequality, but it's very strange.
So you can derive Lebesgue theorem.
I only thinking about infinite sequences. So let me try to say.
But
So
there is a delicate problem in Lebesgue theorem. So if we take just about the statement, I have the question before you give the proof. So you have a point x, and in a real line you can just take interval which contain this x. Or in one-dimensional in infinite sequence, you can fix the prefixes of the sequences.
Yeah.
But we can also consider some kind for binary sequences. We can consider some binary interval, and can consider fix some bits, and also some cone, and then we consider another cone by fixing non-contiguous bits, and it has small probability. This cone, it's kind of small open set containing our point inside our initial neighborhood. But if we just fix some bits in some order, but do we guarantee something for this or not?
I don't understand.
Okay. Okay. Let me draw something. So, let me say this. For interval, we have for line we have a set S, and we consider smaller and smaller intervals. Or on the plane, we can consider just smaller and smaller things.
Yes.
But then, imagine, do you claim that you can find an interval containing our point that in all smaller intervals, including intervals like this and this, the density will be correct. So in standard setting, you have a clearly defined sequence and intervals converging to our plane.
Well, I just said that I have a proof only for infinite sequences. So
And,
I don't know.
But for your proof for Barmalias proof, do we need something like this or not? Or we just
No.
need one specific sequence containing smaller and smaller intervals?
Well, there is like there is like I don't know, but it's like not a plane. That's I'm saying that is a counter space. That's a counter space. So I want to say that starting from some position, all prefixes have density at least 0.9.
Yeah, but all prefixes in some fixed order of bits, yeah? And that's enough.
Yeah, in some fixed order of bits.
You don't claim that if we fix these bits of the prefix and also some bits of in the later sequences, then it will have a high probability. You don't say this.
It's enough to have it for some sequence.
For contiguous fixed bits, yeah?
Yes.
Yeah. And then it can be for binary space, it can be derived from martingale convergence or something like this. That's what you are saying.
Yeah, for example, imagine that I have a set of like, I don't know, 0.9 measure. So, I mean, then it's just I mean, let's say like very, very big, very, very close to one.
Yeah.
But then the point is that if I have if I have a x and I have two possible continuations, then the fraction of my set or of the complement of the set is the average, right?
Yeah.
So it's like a martingale. So if the average is the fraction in some place is most 0.9, I mean, if it's at most epsilon, so that so with probability.
So it's a value of a martingale along a sequence, and martingale convergence theorem requires that they have a limit.
No, I mean, just want to say that with probability 9, for 0.n sequences, it will be at most 10 epsilon. Everywhere. The density will be at most 10 epsilon for every prefix of the sequence for at least 0.9 sequences. Okay, let me try to show. So we want to show that the measure of sets of sequences from my set, where the fraction of the complement is big, we want to say that it's small. So we want to show that it's 0, right?
Okay, maybe we should think about this because no, it's another story, Lebesgue density theorem. It's interesting how it's related to martingales, but we should first think a bit. Maybe we can understand this ourselves, or on that, or if not, we will ask you. It's not just there is two things now to understand, or even three, if we want to show that there is no algorithm that separates inseparable set with positive probability.
No. I mean, what's the problem? You just take, well, you have any set, right? You just take then a finite union of cones that approximate this, such that the symmetric difference has very, very small measure, right? By definition.
Yeah.
So you can assume that it's really you take a large n and you fix all words of length n into the, into plus and minuses. So those that with plus are approximation of your set, and those with minuses are your complement, right? And let's say that in your approximation, you say, okay, let's say the measure of all points that are incorrectly classified is at most epsilon. So it means that for almost all these cones that you say that it's your approximation of your set, the fraction of the complement is at most epsilon. Well, I don't know, 10 epsilon. And then by the martingale inequality, you say that it's also at most 10, I don't know, let's say at most 10 epsilon or at most 100 epsilon for every continuation. For most of the continuation in every position, starting from this point.
Okay, so does anyone understand the proof? I'm confused, but I need to think. Maybe it will become clear. But now I am confused. But maybe someone understood it already. No?
Actually, after 90 minutes of the talk, I cannot understand